For today's lecture, we're going to be talking about a generalized least square theory. Also known as GLS. And for GLS, we're assuming we have a model. Let's say we have a model y is equal to x beta plus some error e, okay? And let's give the dimensions for y as n by 1, x as n by k, beta as k by 1, and our error term as n by 1. Okay, so under our general Gauss-Markov assumptions, we have that the expectation of our error, that's equal to 0, and the variance of our error, okay, that's equal to omega. Okay, now, here, obviously, we say that under Gauss-Markov assumptions that the variance of our error has homoscedastic. But what happens when the homoscedasticity assumption is violated such that we have heteroscedasticity? In other words, we have here the sigma squared. Omega is not equal to sigma squared I, okay? And recall that this omega, this is our variance, covariance matrix, okay? So, if this is the case, then we're implying here that we have some sort of heteroscedasticity. Heteroscedasticity is such a hard word to pronounce going on, okay? Assuming that our Gauss-Markov assumption was not violated, then we know that the beta hat OLS, okay, that's equal to x transpose x inverse x transpose y, okay? Now, for our variance, okay, we can say that our variance of beta hat, okay, this is going to be x transpose x inverse x transpose omega x transpose x inverse. Now, assuming that we have the heteroscedasticity going on in that the Gauss-Markov assumption is violated for that specific term, okay, this variance of beta hat, okay, this is going to be unbiased, but not efficient. Okay, this is going to be unbiased, but it's not going to be efficient because we have this heteroscedasticity issue going on. So how do we solve this? How do we get rid of this? Well, how do we find a way to resolve this? Because in this case, then, even though this is unbiased but not efficient, this is not going to be blue. Okay, so I'm going to say this is not blue, and I noticed I did this in the color blue. Not blue. This is not our best linear unbiased estimator. Okay, why? Because it does not have the smallest possible variance. Okay, so we may ask ourselves then, what is going to be the efficient estimator for beta hat? Okay, what is going to be our efficient estimator for beta hat? Okay, so I'm going to call this here my equation number 1. Okay, equation number 1. We're going to have to do some sort of a transformation on equation number 1 such that it retains beta as a linear parameter vector. Okay, so we need to do a transformation. So we need to do a transformation to retain beta as a linear parameter vector. Okay, so what do we have to do is we need to create a new error term. So this is part A. Let's just say, in order to do this, we need to create a new error term. Okay, let's call this error term V. Okay, which is going to retain the Gauss-Markov assumptions. Okay, and that's including the homoscedasticity assumption. Okay, so if we achieve this, okay, we have achieved a model in which you can get an OLS estimator for beta hat. Okay, welcome back. Okay, so I want you to note that for the case of heteroscedasticity, we're going to have different values, okay, or different variances on the diagonal matrix. So assuming here that we have the matrix omega, this is going to equal to sigma 1 squared, 0, 0, sigma 2 squared, all the way to sigma sub n squared, 0, 0, 0, 0. Okay? So in this case here, we're going to have our sigma 1 all the way to sigma sub n squared values on our diagonals and zeros on off diagonals. This matrix here, we're going to assume or say this is SPD. This is symmetric positive definite matrix. Okay? So here, we're going to assume that our error terms are non-autocorrelated with one another. This is why we have our zeros in our off diagonals for the matrix. Okay. Now, a couple of things to note is that for every SPD matrix, semi-symmetric positive definite matrix, omega, okay, there exists an n by n matrix, okay, such that n by n matrix P, okay, such that omega, this is equal to P times P transpose, okay? So you can think of P as some sort of a square root matrix. So this is going to imply that P inverse, okay, omega multiplied by P transpose inverse, this is going to give us our identity matrix I. Okay, so we're going to do a pre and post multiplication by P inverse to get the result. Okay, in that case then, we're going to have that P, this is going to equal to sigma 1, sigma 2 to sigma sub n, 0, 0, 0, 0, 0, 0. And then we have our zeros on our off diagonals. Okay? So here, notice that on the diagonals, we have our individual standard deviations sigma. Okay? So now, what are we looking for here? We're looking for a new error term that needs to meet the Gauss-Markov assumptions. Okay? So in that case, we're going to come over here, okay? Okay, such that V, okay, this is going to equal to P inverse omega, okay? Now remember that this non-omega sigma, this is going to be our original error term, okay? And therefore, the expectation, okay, of P inverse omega, this is going to equal to P inverse expectation of omega. Now, we know that expectation of sigma, not omega, is going to be 0. So this is going to equal to 0. Okay? Now, what about the variance of it? Okay? What about the variance of it? So coming over here, okay, we're going to say that the variance of P inverse sigma, this is going to equal to P inverse times the variance of sigma multiplied by P transpose inverse. And we know that the variance of sigma, this is going to be omega. So this is going to equal to P omega, P inverse omega, P transpose inverse. And this is going to be our identity matrix I. And now, why is the identity matrix I important? Okay, the identity matrix I is important in that, by the way, this calculation here is from the general rule for variance calculation with matrices. Okay, so you can look that up. Okay, so with this omega, this is the identity matrix, okay, which has the value of 1s on the diagonals, and obviously 1s stay the same. So here we have, this is a trivial representation of homoscedasticity, okay, within our variance covariance matrix. So this would be a great error term to have in the regression because it would meet our Gauss-Markov assumptions in that we have the constant variances of 1. Okay, so now let's go back to our equation number 1 and let's do some transformations okay, in the same manner, okay, using some sort of a pre-multiplication stipulation. So if we do that, okay, so I'm going to say here, recall, okay, from equation 1, we had that y is equal to x beta plus e. I'm going to erase the board, and we'll work on this with a new canvas. Give me 1 second. Okay, so recall, okay, that v, there's going to be, we're going to call this p inverse multiplied by u. Actually, let me make this e, not u. E. Okay, so now we have that y is equal to x beta plus e. Okay, so we're going to apply p inverse here. We're going to apply p inverse here. And we're going to apply p inverse here. Okay, so we're going to take all of this, okay, p inverse y, and we're going to call this y tilde. And we're going to take all of this here. Okay, and we're going to call this x tilde beta. And we're going to call all of this here v. Okay, we're going to make this our error term. Okay? So, something this I'm going to note here is that this beta term, okay, this is still linear parameter vector. This is still a linear parameter vector. That is still a linear parameter vector. Okay? And I'm going to call this here equation number 2. And our error term v still meets, okay, the second part of our requirement for our Gauss-Markov assumption. Okay? So in that case then, we have that y is equal to p inverse, y tilde is equal to p inverse y. So let's actually calculate this out. So in that case then, we're going to have that y tilde. This is going to equal to, so p inverse, okay, we're going to have here is 1 over sigma 1, 1 over sigma 2, 1 over sigma sub n, 0, 0, 0, 0, 0, 0. Okay, and we're going to say this is p inverse, and we're going to multiply this by y1, y2 to y sub n. Okay, we do our matrix multiplication out, and we're going to end up with y1 over sigma 1, y2 over sigma 2, y sub n over sigma sub n. Okay, so this whole thing here, this is our y tilde. Okay, now that we have our y tilde, let's go ahead and calculate our x tilde. Actually, let's just do our x tilde for now, which is p inverse x tilde. Let's do our x tilde for now, okay? Okay, so recall x tilde, this is equal to p inverse x. Okay, now for this x, okay, we're going to have one column of ones, and we're going to have x1, x2 to x sub n. Okay, so obviously the column of ones, that's our constants, and we have our explanatory variables x1 to x sub n. Okay, so we multiply that by p inverse. Okay, so we're going to end up with this being 1 over sigma 1, 1 over sigma 2, 1 over sigma sub n, x1 over sigma sub 1, x2 over sigma sub 2, x sub n over sigma sub n. So this actually ends up being the weighted version of y and x themselves. Okay, so now, okay, therefore all we need to do is we need to apply OLS to equation number 2. And this is going to end up giving us our best linear unbiased estimator based upon our transformations, okay, for model number 1. Okay, so in this case, we're going to end up with beta hat GLS. Now, with beta hat GLS, okay, we're going to have beta hat GLS. Now, we're going to obviously transform our x transpose x inverse x transpose y equation without tilde versions. So this is going to be x tilde transpose x tilde inverse x tilde transpose y tilde. And this is going to equal to x transpose p transpose inverse p inverse x inverse x transpose p transpose inverse p inverse y. Okay, so this is again matrix algebra. And this is going to end up being x transpose omega inverse x inverse x transpose omega inverse y. And I'm going to call this here my equation number 3. In that case then, okay, we're going to have that the expectation of beta hat GLS, this is equal to beta by substituting model 1 into model number 3. Okay? And then replacing y, okay, with x beta plus e. Okay? And just a little bit of note, okay, this is a side note, is that to recall, okay, that omega, this is p transpose, okay, and omega inverse, this is equal to p transpose inverse p inverse. So this is just a little side note here, okay? So if we do that, okay, then the variance, okay, of beta hat GLS, this is going to equal to the variance of x transpose omega inverse x inverse x transpose omega inverse. Now we're going to replace y with x beta plus e. Okay? And this is from model number 1. Okay? That's going from model number 1. Therefore, doing some algebra, we're going to end up with variance of beta hat GLS. This is equal to x transpose omega inverse x inverse. Okay? And now we can say that this here, this is going to be blue in terms of this being our best linear unbiased estimator. Okay? So we can now make the beautiful statement here that the variance of beta hat GLS, this is going to be less than, there's actually more of a proof for this, but we're not going to go into that. The variance of beta hat or less. Okay? And then, therefore, we can go ahead and make the statement that x transpose omega inverse x inverse is less than x transpose x inverse x transpose omega x x transpose x inverse. And then we can put our little QED or our little box here. All right, that is our proof here. I'm going to put this in a nice little box. Just a recall is that we need omega, but we don't know what omega is. Okay, it's the variance covariance matrix with unknown error terms. So omega, okay, just note that in reality, this is the variance covariance matrix of an unknown error term. Okay? So in practice, in order to implement a generalized least squared estimator, we need an estimate for omega and an estimate for p. So in order to do that, we apply what's called weighted least squares, but that's beyond the scope of this lecture, okay? Which is a proxy variance of error term using weighted least squares. So that is it for today's lecture. I hope you've enjoyed it and have a good rest of your day.